Okay, cool. Well, today is the last day, so we'll see how much we can cover. My plan is to finish low latency memory, and then we'll talk a little bit about emerging memory technologies. I'm not going to spend a lot of time, unfortunately, because we don't have a lot of time. And we'll try to start memory interference a little bit, but that's a topic we're not going to be able to fully cover. Does that sound like a good plan? Okay. So let's get started without wasting time. So remember, this is where we were. We were discussing why the memory latency is long, and we talked about the first reason, design of the DRAM microarchitecture, and we discussed some ways of overcoming that. I think there needs to be more work in this area, actually, and I think this is a very open area still of research. The second one is basically we have a fixed latency mindset, if you remember, and we were discussing how to change that mindset by having different latencies for different temperatures, different DRAM chips, and different parts of a DRAM chip. So if you remember the adaptive latency DRAM idea, and also fly DRAM idea that has different latencies for different parts of a DRAM chip, and the solar DRAM idea, we discussed all of those. Now let's go into a little bit more in this direction, and then let's see where this exploration will lead us to. So I think the next question, one of the next questions to ask is, why is there spatial latency variation within a chip? There's certainly latency variation, but some latency variation looked very spatial, right? It was very correlated in the bit lines, for example. And there's a good reason for it, actually, because it's based on the design of the subarray itself. And actually, this paper that I'm going to reference later covers the bigger design of the DRAM chip. It's not just the subarray, but it's the way the DRAM structures are designed. There's some correlation between the location of cells and how fast you can access the cells. So if you look at this structure, for example, there is some latency variation across rows because some rows are close to the sense amplifiers, some rows are far away from the sense amplifiers. If you're close to the sense amplifiers, you're faster because charge flows to you much faster, right? The capacitance is much lower for the charge to travel. I mean, this is obvious, hopefully. That's true for the word line drivers as well. If you're close to the word line driver, you're faster. If you're far away, you're slower. So your distance to these sensing structures and driving structures determines how fast you can be accessed as a DRAM cell. As a result, you get this nice picture of latency variation. Of course, this is logical, depending on the DRAM chips and how they're designed, where the word line drivers are, where the sense amplifiers are. This picture may look a bit different, right? Essentially, you get a picture that looks like this. So there's clearly a very inherently fast region, and there's an inherently slow region in this picture. Which means that ignoring all of the other random process variation, if you know which cells are in the inherently slow region, you can test only those cells, and the minimum latency, minimum reliable latency at which you can access these cells should be reliable for the other ones too. That's the idea over here. If you somehow know this region magically, if the DRAM manufacturer tells you, you just test only that region. So that makes profiling for latency easier because of this spatial variation within the chip. Essentially, the spatial variation, systematic variation in cell access time is caused by the physical organization of DRAM. So I think this is a very good idea. Figure out those cells that are inherently slow, and only test those cells to figure out the minimum latency. But of course, that's the idea of DIVA online profiling, design-induced variation aware. The inherently slow cells are provided by someone, and you profile only slow, memory controller profiles only those slow regions to determine the minimum latency. Of course, you'll tell me that this is dynamic and low cost, and the paper has a lot of detail on how to do this. I'm not going to go into the details of it, but the reason we want to do this profiling once in a while during runtime is because we don't know the long-term effects, right? You may choose a latency, but that latency may not be good 5 years from now, 2 years from now, 3 years from now, who knows? So it's good to do this dynamic optimization. But of course, you can tell me that that's not the entire picture, right? And that's true. It's not the entire picture because the access latency, the minimum latency of a cell is not just determined by where it is. It's also determined by this process variation that we discussed last time. Some cells are slow because they randomly happen to be slow because their access transistors are slow. They have little capacitance, all of those things that we discussed last time. It turns out these slow cells, because of random process variation, not systematic process variation, because of random process variation, they're distributed randomly across the chip. So that's the key realization, one of the key realizations in this work. You have, because of process variation, you have random errors. Because of design-induced variation, you have localized errors. So how do you actually fix random errors? Whenever you see random errors, it's always good to think about error-correcting codes, because error-correcting codes are actually very good at fixing those random errors. Hopefully you get 1 bit per row, for example. And our results show that 1 bit per row is actually, 1 bit per cache line is what you usually get if you get these errors. And essentially, these errors can be fixed by error-correcting codes if you reduce the latency for them. And for these, you do online profiling to find the minimum latency at which you operate DRAM with. And then somehow you figure out, if you figure out your minimum latency this way, reduce the latency to that, and correct the errors that happen in those other cells randomly using error-correcting codes. And that's the idea. We combine error-correcting codes and online profiling. I think last time, one of you mentioned that error-correcting codes would be useful. Maybe we don't use error-correcting codes exactly the way we discussed yesterday, but this is one way of using error-correcting codes. And once you have these error-correcting codes, you can actually use them to back off or figure out the dynamic latencies in some other way as well. So this reliably reduces DRAM latency. Again, I gave you the high-level idea. Exactly how it works is in the paper. And it turns out this leads to higher performance improvements, higher latency reductions compared to adaptive latency DRAM. So if you read this paper says that adaptive latency DRAM may not work under all conditions. And we know that it doesn't work very well at high temperatures. But if you use this sort of profiling, you actually get significant reduction, more reduction in latencies, read latencies. And there's also some section in the paper that talks about the fact that you can actually increase the probability of error correction better by actually shuffling your data or organizing your data in some other way. But I'm not going to go into that. That improves your read latencies even more. And write latencies, you can reduce them even more actually with this sort of profiling. And that leads to even higher performance improvements compared to what we've seen with ALDRAM. That's part of it. And the other benefit of this is this makes ALDRAM more robust now. Because ALDRAM, remember, we said that somebody provides those latencies, two different sets of latencies. There's no online profiling. Now this is an online profiling mechanism to determine the latencies. But here, somebody needs to provide those parts that are inherently slow. So there needs to be more communication between the memory controller and DRAM, as we've been discussing for the past 5 lectures. So this has advantages and disadvantages. A big disadvantage is it automatically finds the lowest reliable operating latency at system runtime, which means that the production time testing cost is reduced. It's actually offloaded to the runtime system, which means that profiling needs to be low overhead in this case, of course. And it reduces latency more than prior methods with ECC. It relies on ECC. It's very hard to do it without ECC. And it reduces latency at high temperatures as well. Again, because one of the big reasons it relies on ECC. The disadvantage is it requires a knowledge of inherently slow regions. Somebody needs to provide them. This argues for, again, a more intelligent memory controller and better communication. And I guess another disadvantage is it requires ECC, but it's already being implemented in DRAM, except it's not just exposed to the memory controller. So going forward, I think there will be more ECC inside DRAM to enable such optimization and also to overcome more reliability issues like VRT. Okay, yeah, and this is, I already said that when I talked about the big advantage, but it imposes overhead during runtime profiling clearly. Any questions? And that's the paper. This is another Sigmetrics paper. It's one of the long papers, actually. Sigmetrics is a nice conference. You can write long papers, basically. There's a submission, there's a page limit in the submission, but then the submissions are actually published in a journal, and the journal doesn't necessarily have a page limit. So you can address all of the comments and improve your paper, make it really solid for publication, as opposed to being bound by a strict page limit that's imposed randomly. Okay, any questions? No? I think there's more work to be done in this area, frankly, to make the profiling overhead lower and even push the latencies to even lower latencies. Okay, let's talk about more complicated things. I think this is interesting, and we haven't talked about it as much. Basically, we're going to make things more complicated. We're going to look at voltage, latency, and reliability and their relationship. And this was the next thing we had done because we wanted to understand this relationship. And I've already given you these numbers, actually. We wanted to reduce the power consumption of DRAM, but in a different way. Not just changing power modes, but maybe trading off between latency and power. So these are actually good papers to take a look at. This is IBM Power 7. More than 40% of the system power is spent on DRAM. In a GPU, more than 40% of the system power is spent on DRAM. And existing DRAM designs help reduce DRAM power by lowering supply voltage conservatively. Essentially, power is correlated with voltage square. You know, the CV square F equation probably. Power is correlated with capacitance, voltage square, and frequency. And if you want to improve frequency, you need to increase voltage. So power is actually has a cubic relationship with voltage. This doesn't do justice to the equation, maybe. And there are some low voltage DRAM, including LPDDR. They reduce voltage by some amount. In this case, we looked at DDR3 because our infrastructure was capable of doing DDR3 at the time. And they reduce voltage relatively conservatively. LPDDR employs some other low power interface. So the key question we want to ask was, can we reduce DRAM power and energy by further reducing supply voltage aggressively? And our goal was to understand and characterize the various characteristics of DRAM under reduced voltage, including latency. We'll look at the latency, voltage, reliability relationship. And we wanted to develop a mechanism that reduces DRAM energy by lowering voltage while keeping performance within a target. Of course, you can imagine other mechanisms. I'm not going to spend a whole lot of time on the mechanism itself. I'll just give you the basic idea. But I think understanding these characteristics is very important for developing future mechanisms. So, okay, basically we had some questions before we started out doing the experiments. How does reducing voltage affect reliability? How does reducing voltage affect DRAM latency if you want to keep the same level of reliability? And how do we design new DRAM energy reduction mechanism? So if you look at supply voltage, you adjust the supply voltage to every chip on the same module today. And we actually designed or adjusted our infrastructure so that we could have a voltage controller. And yeah, you can read the paper for more details. And it's actually on GitHub. This SoftMC version is on GitHub also. So what we did was we tested a bunch of DRAM modules that were manufactured between these years. And we iteratively read every bit in each of the chips on their wide range of supply voltage levels, from 1.35 volts to 1.0 volts. That was where you'll see the error rates. Going below this doesn't make sense, actually, because you get a lot of errors. Okay, so let's take a look at the relationship between error rate, reliability, versus supply voltage for 3 different vendors. And I'm going to show you a distribution of where the different chips lie. So nominal voltage specified by the standard is 1.35 volts. Okay, so these are the different vendors. As you go from right to left, your supply voltage is reducing. And clearly, your reliability is also becoming worse. But it's becoming worse differently for different vendors, as you can see over here. So for this orange vendor, vendor C, you quickly start getting errors when you reduce the voltage to 1.275 in this case, right? For vendor A and B, you actually have a lot of voltage margin. You don't get any errors, basically, until you reach a supply voltage of 1.15 volts. So there's a big margin that they add to their chips for whatever reason, for reliability purposes, of course. But we see that a lot of it is unnecessary under these operating conditions. Of course, operating conditions are important in this case also, and you can read the paper for that. And you can see that there's a gradual increase in some cases, so you can actually take advantage of this also. We'll see that there's spatial variation. Also, some banks are very reliable at even voltages like this. Some banks are very unreliable because of the way voltage varies and voltage is supplied to different banks. Okay, so you can see that there's a Vmin, minimum voltage without errors, for different vendors and different chips. And these bars are actually the distribution of different chips. And you can see that errors are induced by reduced voltage operation. And reducing voltage below Vmin causes an increasing number of errors. Okay, so hopefully that's obvious. And later we wanted to understand this clearly. Whenever you want to understand, you build a circuit model also, because you cannot examine exact bits in DRAM and how the circuit behaves. So we have the circuit modeling using Spice, and that's also open source. You can download it. And this is how we model the circuit. Essentially, this is supply voltage on the x-axis, and this is the latency for activate and pre-charge that we changed. So, and this plots the reliable latency that you need to use to get no errors. So if your supply voltage is 1.35, that's nominal voltage, you use the latencies that are specified. Basically, you can operate at low latency because you have high voltage, right? Your charge sharing is faster. But if your supply voltage goes down to 0.9 volts, you'd better increase the latencies because it takes time for the circuit to share the charge, get sensed. Everything is basically slower when you have low voltage. Now this is obvious. That's how actually we increase the frequencies, right? At high voltage, you can increase the frequency. So you get this, the shape of this, this type of curve. And this makes sense. So, but this exposes the trade-off also. Basically, you can operate at very low voltages. You just need to increase the latencies, right? That's the idea. Now, this is about low latency DRAM, but there's a trade-off between latency and voltage, as you can see. Or the opposite end is also true. If you want to operate at lower latencies, maybe you keep increasing the voltages. Of course, this curve flattens out at some point because the DRAM is not designed for that high voltages also. You don't gain much benefit. So it's good to think about this curve. But this curve is purely based on the circuit model that we built. Okay, basically the takeaway is reliable low voltage operation actually requires higher latency. That's one way of correcting the errors. Of course, you can say I correct the errors with ECC also. That's another possibility, but I think that's an expensive mechanism. This may be a cheaper mechanism. And I think maybe there are multiple different combinations of mechanisms that could be useful going forward. Latency is one way of correcting the errors, increasing the latencies. Okay, so this is circuit simulations. We can verify it with our infrastructure also. So you'll see that the curve is going to be similar in real chips. So this is the curve that you see in real chips, actually. This is supply voltage, and this is the measured minimum activation latency in this case. Pre-charge latencies are in the paper. And you see that the curve has a similar shape, right? If you go back here, the curve looks like this. If you go here, the curve kind of looks like that also again. So what does this mean? Basically, this is for some vendor, I think one of those vendors, A probably. These are density plots again. This means that, okay, I think basically this means that 100% of the modules are operational correctly at 10 nanosecond activation latency at this voltage. And you can see that until you get to 1.10 volts, 100% of all of the modules that we've tested are operational with 10 nanosecond latency. Now, if you get to 1.10 volts, 90% of the modules correctly operate if your latency is 10, but 10% of the modules require 12.5 nanosecond latency. And the reason we jump up by a step of 2.5 nanoseconds is because that's our minimum granularity of increasing the latency or changing the latency. If you have a better FPGA infrastructure, you could be finer grain, of course. And you can see that as you go to the left, now only 50% of the modules become operational at this point of voltage, and only 20% of the modules are operational at this point of voltage at 10 nanoseconds. But you can see that there is still a significant fraction of modules that are operational if you keep increasing the latencies. At 12.5% for nanoseconds, for example, 30% of the modules are operational. And some of them actually have too many errors to fix, even if you increase the latencies. So you can actually adapt to this characteristic, and you can keep pushing the voltage down. Okay, we already discussed this. It's nice that the real chips actually follow the circuit level modeling that we've done also. Okay, I already discussed that also. And the DRAM requires longer latency to access data without errors at lower voltage. You may not be always able to satisfy that, but for some modules, you're able to satisfy that in this case. Okay, so that's one of the observations. There's a lot more detail in the paper in terms of how data patterns affect this, how temperature affects this. If you're interested, you can read this paper also. Okay, and this is also interesting. This shows the spatial locality of errors. So this is one module at some voltage reduction. And this shows the distribution of errors in different banks and different rows. And you see that there's a significant spatial variation in the errors. So this is the probability of row with greater than or equal to 1 bit error, more than 1 bit error, as you can see. And you can see that it's a density plot again, like we've seen in the past. you can see that only 3 banks have errors. Everything else don't have errors. And within the banks, you have a pattern. Not all rows have errors. It turns out that in this bank, some other rows don't have errors, right? So we don't quite understand this, actually. It's probably due to the way things are designed, and it's also probably due to the way voltage is routed, but there's also probably a random component in it, because we don't know how exactly power is routed in DRAM. It's not disclosed to anyone, as far as we know. That's one of the reasons why building these DRAM chips and completely modeling them is also difficult. But there's certainly some random plus systematic component going on here that we don't fully understand at this point. But the takeaway is errors concentrate in certain regions, and you can profile for this. If you have an intelligent memory controller, again, an intelligent memory controller can figure all of this out. It's not that hard. It just takes time, and you need to develop simple profiling methods. But we've been discussing profiling for some time. Maybe there are ways of reducing the cost of that profiling. Okay, so basically the summary is voltage-induced errors increase as voltage reduces below some Vmin. Errors exhibit spatial locality, and increasing the latency of DRAM operations mitigates voltage-induced errors. So can we actually take advantage of these observations? And the answer is yes. You can exploit the trade-off between voltage and latency to reduce energy consumption. You could, of course, do other things, but this is what we did in this work. And we wanted to reduce DRAM voltage reliably. If you actually want to violate that reliability part, you can do even more. Maybe if your application is tolerant, for example, if you're running a neural network, you can violate that even more, and you get some unreliable execution, but maybe you know the error rates and you can adjust. Okay, but in this case, we didn't do that. We basically said we want to reduce DRAM voltage reliably without any errors, but we're going to increase the latency at lower voltages, so we'll get some performance loss necessarily, right? And let's take a look at that performance loss. This is the supply voltage on the x-axis, and this is the DRAM power savings that you get, and this is the performance loss that you get. This is, of course, modeled. Basically, here we pick the minimum latency that still keeps us operational for a given DIMM at a given voltage, and the latency increases, of course, as you go from right to left. That leads to some performance loss. But that also leads to some power savings. So clearly, there's a trade-off between performance and power in this case. And we don't want to be operating here because we do save a lot of power, but we lose a lot of performance. So we need to have a mechanism that controls the system. Okay. And in this case, my students aptly named it Voltron. I guess they like watching these. How many of you watched Voltron in the past? Nobody knows about Voltron? You know, but you didn't watch. Interesting. That was not popular during your times, or you guys are too young? Yeah. Yeah. If you search for Voltron, it's a cartoon about, what is it about? These robots coming together and forming the Voltron, and they're much more powerful together. Okay, it's an old cartoon. I didn't realize that my students were much older, or somehow this is a cultural thing. Maybe that was popular in the US or something like that. I don't know. Okay, anyway, basically, this is the overview of the mechanism. I'm not going to go through the details of this a lot because this is one mechanism you can build. But basically, someone specifies some performance loss target and inputs that into the system. And the system selects the minimum DRAM voltage without violating that target, hopefully. That's the idea. It's like any control system that you build, and then you need to develop a control system in between. So one of the things that you need for this is you need to predict the performance loss due to increased latency under low DRAM voltage. So there's a model, performance model, that Voltron needs to incorporate. And in this case, the performance model is based on a linear regression model. In general, I don't like these sort of regression models, but that's okay. This is a proof of concept because it's not clear if they always work. Basically, this regression model takes applications characteristics, and the paper specifies what those are, like memory intensity, for example, is one example, and takes DRAM voltage. It basically tells you the predicted performance loss at these different DRAM voltage levels, such that you can pick the lowest voltage that satisfies the performance loss target. Of course, you need to train this model. It's like any statistical or machine learning model. You need to train this. And in this case, we do offline training of the model to figure out how the application characteristics and DRAM voltage affect the performance loss. That's the idea over here. And then you basically compare that to the target, and you pick the final voltage as a minimum voltage. Okay, I think. So what are the characteristics? This is one way. Of course, there are many, many performance models that you can build. In this paper, we look at memory intensity and memory stall time. Those correlate with your performance loss at different latencies, of course. These are both affected. These are things that affect the application's performance if you change the memory latency, clearly. And of course, you need to handle multiple applications somehow. That makes things hairy. You predict a performance loss for each application in this case, and you select the minimum voltage that satisfies the performance target for all applications. So in this case, you need to be conservative, basically. Of course, you can think about other ways of dealing with this, right? If you map applications to different channels, you can actually adjust the voltage of these different channels differently, such that the applications don't affect each other. Or you could group the applications such that applications that are happy with a particular level of voltage go to the same channel, right? These are ideas that we don't explore. But I think in a real system, if you're building it, you should really be exploring this sort of ideas, as opposed to forcing all of the applications to go together in the same channel and ensuring that the voltage is lowered such that no application's performance is violated. It's better to group the applications somehow to different channels. And maybe if we have time, we'll get to the memory channel partitioning idea. That's an idea we had looked at a long time ago in 2000 or so, and it was published in Micro 2011. The idea is memory channel partitioning. You group the applications that do not interfere with each other badly and put them in the same channel. So you partition the channels across the applications. But you could use similar principles for voltage as well. Okay, so a comparison to prior work. It's actually interesting because it's our own prior work. A long time ago, with Intel, we looked at reducing the memory voltage and frequency. And if you're really interested, this is one of the earliest papers on memory voltage and frequency adjustment. And basically what we did over here was we dynamically scaled the frequency and voltage of the entire DRAM based on bandwidth demand of the applications. Now, one of the downsides of what we had done at that time is essentially you have this off-chip channel, and we lowered the voltage on the peripheral circuitry, which is here basically. And once you lower the voltage here, you actually need to reduce the channel frequency as well, which is not good because that affects your bandwidth. In contrast, in this current work, based on the understanding we developed, what we do is we keep the peripheral circuitry voltage high, so we don't affect the bandwidth. But internally, we can change the voltage of the DRAM array. That's the idea. So here you affect the bandwidth. Here you don't affect the bandwidth that's coming off the chip. And also on top of this, we exploit the spatial locality because we hadn't realized that at that time. And actually, once you actually change the voltage only here, you can basically have different voltages for different banks and operate the different banks at different latencies. Of course, these increase the complexity in the memory controller. Right now, the memory controller needs to have different timing parameters for different banks. But that's how we explore new ideas in simulation again. Okay, the benefit is now you get higher performance because these banks, basically these banks can still operate at low latency because they don't see errors at the voltage level. But this bank needs to operate at high latency because it sees errors at that voltage level. Okay, so we evaluated this with a bunch of workloads and also simulators. And you can find the simulator as we discuss its RAM later. And we compared to our prior work. And these are the results. Essentially, these are the energy savings that you get with the control mechanisms that we have. And I don't think it's the best mechanism, but it provides you still energy savings, as you can see. It's CPU plus DRAM energy savings. So the past work works well if the applications have low memory intensity. The reason is because, well, it works well, meaning that it saves some energy, but not a lot, as you can see over here. This actually, we actually measured this on real systems in our ICAC 2011 paper. We had this experimental board that we built with Intel together, and we measured how you can do this scaling on a real board. So these are commensurate with the results that we have from the real systems. You don't save a lot of energy, but it's a real system energy savings, an entire system energy savings. So once you have high memory intensity, that past work doesn't work really well because it's designed to lower voltage and frequency when you don't have high bandwidth demand. Clearly, high memory intensity means that you have high bandwidth demand. On the other hand, actually, Voltron gives you even higher energy savings at high memory intensities because that's where actually you don't change the bandwidth of the system a lot, but you reduce the energy significantly. And reducing the energy when you have high active power is actually much more beneficial. Okay, so what about the performance target? So clearly, this is a trade-off between power and performance. And we specify the performance target to be 5%. Of course, this depends on your tolerable loss on performance. And we found out that on average, the performance is reduced by 1.8%, as you can see in this case. Actually, the maximum performance loss is about 3.2%, and you can find that in the paper. So even this simple control system satisfies the performance target while saving a lot of energy in the entire system. Okay, any questions? Okay, let's go into advantages. So clearly, this enables a new trade-off space. You can trade off between voltage and latency to improve energy or performance or something else. You can exploit the high voltage margin present in DRAM. The disadvantage is now you need to do even more profiling. Basically, you need to find the reliable operating voltage for each chip, maybe not only each chip, it's also each bank, right? And this leads to higher testing costs, either online testing or offline testing, depending on when you're doing this. And maybe there are some other disadvantages. I didn't want to put the mechanism as a disadvantage, but there could always be other mechanisms that you can build. Yes, please.
Did you consider the power needs that are required if you actually want multiple voltages? Is this covered at all?
Like what kind of regulators that you want? Yeah, we didn't really cover that as much. We assumed that you could do it basically in this case. So there may need to be more cost to enable this. But that's a very good point. Yeah, you need some voltage regulation, for sure. But that affects, I think, if you want to have different voltages to different banks, for example. If you want to have a single voltage to all of the banks, then you're fine. Any other questions? Okay, so let's move on. And this is the paper, actually. This is a long paper, also another Sigmetrics paper, as you can see. Maybe I should assign one of these Sigmetrics papers. I'll ask you which paper to assign. Are these interesting to assign, you think? Okay, we'll have a vote later on in terms of which papers. Because I promised that I will assign only 8 papers. We can violate that and go to 10 if you want. We can violate that margin. Okay. Okay, so I will not answer this question, but I think there is a lot more to be done if you answer this question. So far, everything that we've done doesn't sacrifice reliability. We try to keep everything completely reliable. But what if you can sacrifice the reliability of some data to access it with even lower latency? Right? Then I think this opens up even more opportunities. Because according to our results, we know the error rates that you would get depending on what latency or what voltage you're operating with. And maybe there are some applications or there's some data that is okay to operate at that error rates, and you may push the boundaries of the performance, latency, and voltage even more aggressively if you know what error rates you can tolerate, and if you know what latencies or what reduced latencies and what reduced voltages can satisfy those error rates. I think there's a lot of potential over here. Okay, so let's switch gears a little bit. I'll talk about these relatively briefly because we don't have a lot of time. I'd like to cover the emerging memory technologies also, but I've already given you some of the ideas. So later, as we develop this, let's say, understanding of latency reliability relationship, my creative students realized that you could do even more with this relationship. And that's the idea of supporting more security primitives. And security primitives that we're going to support are true random numbers. I've already given you the basic idea here, but we're going to go into a little bit more detail. Not full detail, because the paper actually covers a lot of ground here. We're not going to do the statistical analyses that the paper does, for example. You can also support physically unclonable functions. I'll give you a little bit more on this one as well. And if you change DRAM, you can quickly destroy in-memory data also. I'm not going to talk about that, but you can find the paper online. This is another paper, interestingly, that keeps getting rejected. Partly, it's not very well written. I'll admit that part. But the second part is somehow people think that DRAM manufacturers will never do it. Again, if you don't put it out, they will never do it. Yes, you can guarantee. So we put it out in archive. You can read the archive version. Okay, so let's talk about this one. I find this fascinating, I think. You can generate random numbers at very high throughput and low latency using the observations that we've just discussed, actually, in terms of latency. I think I've already said this. High throughput through random numbers enable system security and various randomized algorithms, and the paper has a lot of references related to this. Many systems actually use random number generators. Some of them have true random number generators. Some of them don't. But some systems don't have true random number generators, but they have DRAM devices because they don't afford the cost of a true random number generator, especially IoT, mobile, and embedded, where security is actually very important going forward. So basically, DRAM is a good substrate to enable security functions because it exists everywhere. Right? If you could actually change the DRAM slightly to make things more secure or enable some security primitives, you can take advantage of it everywhere DRAM is employed. That was one of the goals that we had. And we looked at current DRAM-based true random number generators, and some of them actually do not fundamentally sample a non-deterministic entropy source. Very quickly, I'll give you the basic idea. Some people have proposed that if you measure the latencies of accesses in DRAM, you'll get random numbers. Because memory scheduler behaves, according to them, they don't say non-deterministically, but you basically get random numbers if you do this measurement. I think those are pseudo-random numbers maybe because we don't fully model the phenomenon. I'm not sure if those are true random numbers because in the end, memory scheduler is really deterministic, right? It really doesn't have non-deterministic effects that is affecting it. It's really a deterministic thing, and that's what this means basically. I don't think looking at latencies coming out of the memory scheduler is a good true random number generator. But some other phenomenon in DRAM, like the failure rates that you get if you increase the refresh interval, that leads to random numbers. Basically, you increase the refresh interval and see which cells fail. And the pattern of failure, you can read those cells that fail. Some of the cells fail randomly at some refresh intervals, 50% of the time. You increase the refresh interval to 10 seconds, for example. Some cells fail at a 50% rate. And you can see the values in those cells and construct a random number out of that. That's the idea. But this is too slow because you need to wait for a long time, increase the refresh interval. So our goal was to have a new and effective true random number generator that uses commodity DRAM chips without any changes to the chip to provide random values with high throughput, low latency, and low interference to the system. And the idea is I think once you have seen all of the results that we have, the idea is very simple. You reduce the DRAM access latency below reliable values and exploit the DRAM cells' failure probabilities to generate random values. Now, what does this mean? This means that there are some cells that fail with 50% probability. You need to find them. So you need to have a profiling mechanism that finds these cells that fail at 50% probability when you reduce the latency to some level. So there needs to be a profiling mechanism. And once you find those cells, and if those cells are reliably failing 50% of the time, every time you access them, that's great because that's a random number generating cell. And whenever you need to generate a random number, you access those cells at those latencies, and you get a 1 or 0. That's a random bit. And if you need a bigger random bit, you access those cells multiple times, or you access many of these cells that have the same property across the DRAM. So that's the idea here. I think I've given you the basic idea. And it turns out this is true in real DRAM chips, and it gives you a random number generator. You can construct a random number generator that's high throughput, much higher throughput than previous random number generators that are DRAM-based, and much lower latency than previous random number generators that are DRAM-based. So let's take a look at this in a little bit more detail. I don't know why PowerPoint does this. This is really annoying. You can see that this is slide 38 out of 8. It somehow is not able to, I guess, propagate some changes. Okay, latency failures come from accessing DRAM with reduced timing parameters. A cell's latency failure probability is determined by random process variation, as we've seen. And some cells fail randomly. And we want to find those cells. We want to explicitly profile for those cells. Randomly means 50%, according to our definition. So why does this happen? Let's take a look at it. We've seen this before, but I'm going to put this in more context. So this is our cell. Remember this time versus bitline voltage. Essentially, whenever you do an activate, this is the voltage that you have on the bit line, right? Assume that the cell is charged, and whenever you do an activate, the charge is shared with the bit line. So bit line actually has some charge perturbation, and sense amplifier gets enabled to detect that charge, and sense amplifier really drives that charge to VDD in this case because it senses that it's a positive perturbation. And you can read the cell at this point. That's the activate to read delay. And you've seen this before, that's TRCD. And there's some ready-to-access voltage level, actually, that happens even earlier. TRCD has a lot of margin, as we've seen in prior work. There's an earlier voltage level that's ready to access actually over here. So there's a huge guard band in TRCD or activation latency, as we've seen also before. That's the timing margin. But because of process variation, this curve is not the same for all cells. So you can see that different cells have different curves. That results in cells having unique behavior. And there are some strong cells, as you can see. They become ready to access earlier. There are some weak cells. They become ready to access much later. So the margin for those weak cells is lower. But my point here right now will be this. If you reduce the latency to some level, you see that there's a probability distribution over here. There are some weaker cells that have a higher probability to fail. There are some stronger cells that have a low probability to fail. But there are some cells in the middle that have 50% probability to fail. Of course, this curve doesn't show the probability of failure, right? You need to do this testing many times to figure out what's the probability of failure. This curve doesn't show, but I've given you an example in the refresh. When we talked about the Reaper paper, I've given an example of the failure distribution probability of different cells. It's very similar in this case. When you reduce the latency, you have a failure probability. Every time you test a cell, you have a failure probability. And if it's 50%, that's a good random number generator cell. And we're going to pick those cells that fail with 50% probability. So there are some cells that fail always, let's say, when you reduce the activation latency. There are some cells that fail never when you reduce the activation latency. We don't want them. What we want is those cells that fail randomly when you reduce the activation latency to some level. And for that, you need a profiler. You can do an online profiler again. And I think online profiling is very important for this again. So those are called RNG cells, random number generator cells. And the paper talks about how to find those cells, whether those cells actually lead to random numbers, and evaluation of the random number generator. I'm not going to go through all of the details of how you implement this in the system. I'll give you the basic idea. If you're interested, you should really read the paper. So basically, we generate these random values by repeatedly accessing these RNG cells and aggregating the data red. So there are RNG cells in different banks, for example. If you want to capture a 64-bit random number, and you have 8 banks, you find 1 bit, let's assume 1 bit, in all of the banks. So you gather 8 bits in one cycle from each of the banks, and you do 8 accesses. That gives you a 64-bit number, right? So, and it turns out the random data satisfies the NIST statistical test suite for randomness. There are a bunch of randomness tests that National Institute of Standards and Technology has developed. Actually, every country has their own randomness tests. I think Germany has also its own random number generation tests. We didn't test it with the German version. We tested with the NIST. And it turns out the generate random numbers. It satisfies all of those tests, basically. And the throughput, again, I'm not going to go through the detail of the throughput, but you can find in the paper. The throughput is relatively high. It's not as high as if you have a random number generator on chip. Latency is also very low. It's less than 1 microsecond, but if you actually are aggressive in getting these random bits, then you can actually reduce the latency. And power is actually also very low. It's actually, if you look at the power for generating a random number, when you change the refresh rate, you need to wait for so long to get a random bit, because the refresh, you need to ensure that the data leaks randomly. The power is, I think, in the order of milliseconds when you actually do it with a refresh. But here, in this case, it's really nanojoules. It's very small. And unfortunately, I don't have many slides over here. But is this interesting? Yeah. If it's interesting, I would recommend reading it. Should we assign this as required reading? Some people say yes. Some people are skeptical. OK, but this is definitely in the list of optional readings, like everything else. So feel free to read it. And I think there is more work to be done in this area to actually use it in real life. Okay, so let me switch to the next one. And this is the paper, actually. Let me switch to the next one. The next one is developed by the same authors, actually, as you can see. It's actually the same phenomenon that we're going to exploit. When you reduce the latency, you get errors. In the previous case, actually, this is earlier work. The random numbers came later. In the previous case, in the random number generator, you wanted to find these cells that fail at 50%. But if you want a physical unclonable function, this means that you want to identify a device uniquely. So there are some cells that fail always, and that gives you a unique pattern for that device. That's unique across devices, essentially. So you want to find the cells that fail always when you reduce the latency, and that is a unique signature of the device, because that signature doesn't overlap with any other device's signature, it turns out. So that's the idea over here. It's a completely different profiling mechanism. It exploits the same underlying phenomenon, but it's a completely different profiling mechanism and completely different evaluation mechanism, because you need to show that things are unique in this case, not things are random. Okay, so let me give you the executive summary. I'm not going to, again, go into a lot of detail, but what is the motivation for a physical unclonable function? It's really used for authentication. So you can authenticate a system via unique signatures if you can evaluate a physical unclonable function on it. And physical unclonable function means that you execute a function that's not clonable in some other way. It has physical characteristics, but it's not clonable. And if you're interested, you can read the original paper, Physical Unclonable Functions. And signatures, or puff response of that function, reflect inherent properties of a device that cannot be replicated if you have a good physical unclonable function. It should be unique to the device and just that particular device. Some other device should not have the same signature if you send the same challenge to that device. And DRAM is a promising substrate for physical unclonable functions because of the same reason we said for random number generations, right? It's widely used. It's everywhere. People currently add the physical unclonable function circuitry inside the chips, for example. But you don't need to do that if you can use DRAM as a puff substrate. Of course, we're not the first one to think of DRAM puffs. Actually, other people thought about using puffs in DRAM. Some of them are based on our work in refresh, actually, which is really interesting. And the refresh-based DRAM puffs, again, retention-based DRAM puffs are interesting. Some of them actually use row hammer. Some people find that the bit errors that you induce because of row hammer are unique to the devices. And they say that, oh, you could use this as a puff, physical unclonable function. But then there's some other work that I've seen that we reference in the row hammer paper that attacks this puff, showing that that's not unique, or uniqueness properties are compromised. You can read I think if you're reading the row hammer paper, which you should be, you can find those references. But current DRAM puffs are very slow, meaning that you can actually do this by increasing the refresh interval, and the failure pattern of some of the cells, you again need to profile the cells. You need to profile the cells that actually fail all the time and find them. And the failure pattern that you get is unique to the device. But this is very slow again. Some of the other works require DRAM reboot. What does this mean? This is actually very interesting, I think. If you actually reboot your DRAM, and without doing anything to the bits, just read the values, startup values they're called, it turns out you'll get a random, not random, a unique failure pattern if you choose the bits correctly. Or they require additional custom hardware, which I'm not going to go into. But of course, if you want to identify your device, requiring a DRAM reboot is not very good, right? Because that takes you offline for some time. Okay, so we wanted to develop a new and effective puff for existing commodity DRAM devices, again with low latency and low system interference across all operating temperatures. So one of the things that we didn't discuss with refresh is very much affected by operating temperatures. So if your temperature is changing a lot, both in the random number generation work and the puff work that relies on refresh, you have a problem. We'll see that in this case. The key idea of the DRAM latency puff is that you reduce DRAM access latency below reliable values and exploit the resulting error patterns as unique identifiers. Again, you need to pick those bits that fail all the time. And in this case, we had characterized a smaller number of chips because it's older work. And it turns out you can evaluate this physical unclonable function with very low latencies, 88 milliseconds, and its speed up is much higher compared to prior DRAM puff evaluation mechanisms. So you can see that the speed up is higher at lower temperatures because the prior DRAM puffs rely on retention time. And if you have lower temperatures, it takes a longer time to get errors, right, when you increase the refresh interval, as we know very well by now. Let me give you a little bit more into this because this is, I think, interesting. How many of you know about puffs, physical unclonable functions? Okay, some of you. Have you worked on them? Okay, but you know of the concept, what they're used. I think it's fascinating, actually. People devise a lot of puffs. So essentially, we want a way to ensure that a system's components are not compromised. And physical unclonable function provides a function that you evaluate on a device to generate a signature that's unique to the device so that you can actually build some protocol on top of this physical unclonable function that ensures that the system's components are not compromised. So we refer to the unique signature as a puff response. And the protocol that we build on top of this is called a challenge response protocol, CRP. So essentially, you need to do this communication. There's a trusted device, and there's some device that you're communicating with over the network somewhere. It doesn't matter. It could be on the same system also. Maybe somebody swaps out this untrusted device, right? Who knows? So trusted device basically sends a challenge to the untrusted device, challenge X. And the untrusted device evaluates a puff based on this challenge and sends a response, puff response back. And the trusted device checks whether the puff response is correct. Of course, somebody needs to register these challenge response pairs in the trusted device beforehand and then distributes the devices. There's, of course, security issues related to that, but we're not tackling here. Our goal here is to design the puff that can be evaluated. When you receive a challenge, you start evaluating the puff, and we want to do this very fast. That's the goal over here. We're not concerned with how you design the protocol. There's a lot of higher level work that is concerned with how you design the protocol. Okay, so if the puff response is correct, the trusted device now can trust this previously untrusted device because it's authenticated. And it doesn't need to, maybe you don't believe that one challenge is enough. We keep sending multiple challenges, maybe 100 challenges. And the device, if it gets all of them correct or some threshold number correct, then you basically authenticate the device. That's the higher level protocol. Here we are concerned with making this really fast. Okay. So actually the paper has, maybe I'll cover it if we have time at the end, but the paper talks about a lot of characteristics that we want from a puff. And I would recommend reading the paper because we actually gathered a lot of characteristics that people talk about in different papers and examine them methodically in the paper. On top of the characteristics, for example, one of the characteristics is the different devices should be unique, right? They should really have unique signatures. If you have overlap in the signatures, then there's a problem over here. And you should not be able to imitate a device in some way. That's the physical unclonability. Somebody can swap this device with some other device. That means that you should not be able to clone it somehow and imitate that, the challenge response pairs. That's the idea. So there are a bunch of these characteristics. One of the other characteristics is runtime accessibility. I think this is really important. This should be, basically the puff should be evaluated quickly with minimal impact on concurrent applications, especially if you want to do this authentication often, right? Why do you want to do this authentication often? Because I think in the connected world today, we may have attacks that swap the system components with malicious parts. And you want to defend against those attacks, which means that you may want to do this authentication relatively often. Okay, and DRAM, I think, is a promising substrate for evaluating puffs because it's everywhere in modern systems. And we've already discussed this. Current DRAM puffs are slow, and they get exponentially slower at lower temperatures. And I'll show you real results with this. So what we did was we found out that latency failures come from accessing DRAM with reduced timing parameters. You already know this. And a cell's latency failure probability is determined by random process variation. And some latency failures patterns, not all cells, of course, as you know already by now, some latency failures that you see in some cells are repeatable and unique to a device. Essentially, I've already said that. We can provide repeatable and unique device signatures using latency error patterns. So this is the key idea again. There are some cells that are that have high percentage chance to fail. There are some cells that have low percentage chance to fail. And we want to identify these cells that fail all the time at a given TRCD, to compose a puff response using DRAM cells that fail with high probability. So it's a different profiling process. Okay, and you can read the paper for more details of this. The paper shows that the latency error patterns based on the selected cells satisfy the puff requirements that we outline in the paper. And it turns out the latencies are very low. It's 88 milliseconds. Let's take a look at this evaluation latency. So this is directly from the paper, from real DRAM chip tests. And our infrastructure was able to test between 55 degrees to 70 degrees Celsius in this case. And this is the evaluation time of a physical unclonable function. And this is DRAM latency puff. That's the proposal that we have in this paper. It's constant basically across temperature because latency errors actually don't depend on temperature, at least in the intervals that we've tested. It turns out it's fast and constant latency. And of course, to be able to generate a puff response, you need to look at a memory segment. And that memory segment determines how fast you can generate the puff response because that determines how many bits satisfy this property. As you increase the memory segment, you actually get more bits. That's true for the random number generation also. If you look at a bigger segment of memory, you'll get more cells that are random number generated cells. But of course, you want to minimize the memory segment because you don't want to waste memory because you're really using it just for puff in this case or just for random number generation in the previous case. Let's take a look at the prior work. This is DRAM retention puff. I think it's a neat idea for sure, but it's just too slow. Basically, if you use the same memory segment size, you need to wait a lot to evaluate the physical unclonable function. That's basically much slower, as you can see over here. Of course, at high temperatures, retention leakage is much faster, and you can see that the evaluation time reduces exponentially. That's exponential, as you can see, because you have a log scale over here. So this is still very slow at 70 degrees Celsius. And ideally, you don't want to operate here, right? You want to operate at low temperatures as much as possible. Okay, so if you increase the memory segment size, you actually get better because now you actually get more cells failing. So we make the memory segment 64 kilobytes here, kibibytes, I guess. But it's still slow, and that's also slow. If you increase it even more to megabytes, it's still pretty slow, actually. So you get about 10x. Of course, you could be increasing the memory segment size over here, which you didn't do. And this, the manufacturers have similar behavior. This is manufacturer B, and this is manufacturer C. So it's really interesting to see in real devices. This is averaged across many devices, of course. Overall, it's 223. And in the end, basically, you get, assuming the same memory segment size, which I believe is 64 kilobyte here, you get about 2 orders of magnitude speed up in the puff evaluation time. I think that's the beauty of using latency as a way of inducing errors. If you use retention time to induce errors to get some patterns in your device, whether to generate random numbers or to use puffs, to generate puffs or do something else that I don't know of yet, it's just too slow because retention is a very slow process. Whereas latency is a different lever, right? You reduce the latency, which is fast. You're actually making the device faster. And it's actually giving you errors. And now you can mine those error patterns to generate random numbers or physical unclonable functions, whatever you want. I think that's the key realization. That's the fundamental realization. Playing with latency is much faster than playing with retention times. And also, I think fundamentally, we want to get rid of refresh, right? We don't want to use it for some purpose. And also, we want to reduce the latency. And if it buys us some other benefits, that's great. That's another way of thinking about it, I think. In general, this is in line with reducing the latency is in line with everything we want to do in the system. Okay, there are a bunch of other results in the paper, and you can read the paper. Actually, this is true for the random number generation paper also, but there's a detailed analysis on device of 3 major DRAM manufacturers, the evaluation time of a puff, how to optimize retention puffs. We actually optimize the retention puffs quite a bit to improve their performance, but it's fundamentally slow. System interference, and there's an algorithm to quickly and reliably evaluate the DRAM latency puff, and there are a bunch of design considerations. There's actually a lot of statistical analysis also. I just omitted that because you need to do a lot of statistical analysis to show that you really satisfy the puff requirements, which is somewhere over here. I don't find it though. Yeah, there you go, the first one. The first one requires a lot of statistical analysis actually over here. because you want to make sure that what you're getting is really a puff. Okay, and that's the paper. And there's a lightning talk video, but not the full video. I don't know why. Any questions? Yes, please.
Do those responses to those challenges change, for example, due to aging?
So that's a great question, I think, in general. We didn't really answer that question in this particular work. I think for short-term aging, they don't, based on our results in other works. But for long-term aging, we don't know. And I think in general, if you want to employ these in the long term, you need to reprofile. So basically the solution to all of those aging related questions and temperature related questions is really reprofiling once in a while. That's why profiling is very important, I think. And that's why you need an intelligent controller. Yes?
I have a more fundamental question regarding this whole latency stuff. Did anybody ever look into if a sense amplifier can be built in a way such that it tells you when it has finished sensing?
Yeah, that's a good.
I mean, fundamentally you try to profile these different cells, but if you just have a sense amplifier that tells you, okay, now I'm done, I have the data,
Yeah.
you wouldn't need any profiling, it would work on every temperature range, but I guess you have some area overhead.
Exactly, yeah. I think people have looked at that in the past, but existing DRAM doesn't do that.
Okay.
It's, I agree with you. I think that's actually a very nice way, and people should look at how to reduce the area overhead of that kind of sense amplifier. Then you can actually make the interface more asynchronous, right?
Yeah.
Right now, you're relying on a synchronous interface.
Of course, I mean, this would ensure much more changes
Exactly,
and
yeah.
everything, but
Yeah.
I think it's just a natural way to think about the problem. You want to know when you're done accessing the memory, and
Yeah.
to build some form of breach detection would.
Yeah, I think in the past, a long time ago, DRAM interfaces were asynchronous, and then they moved to synchronous interface because it was easier to deal with.
Okay.
SDRAM, for example, means synchronous DRAM. There's a reason why it became SDRAM. I think it should be reevaluated, frankly. It should be reevaluated, but it's not an easy evaluation to do, frankly.
Yeah.
If you would like to do it, feel free. There's some room for innovation there. I think the difficulty is how to make the sense amplifier small enough, how to minimize the noise and all of that, and how to minimize the overhead of this asynchronous interface. But I'm very open to this sort of approaches, for sure. But if you work on this area, you will get reviews saying that DRAM manufacturers will never do that. That's fine, I think. You just say, okay, thank you, and move on. Because I think the same reviewer said to us, Rowhammer doesn't exist. Yes, please.
Regarding the generation of random numbers, is there any difference in the quality that you can observe if you investigate the different vendors?
So that's also a very good question. There certainly is. Yes, basically. The paper has a lot more detail. We look at ABC vendors. And for example, two of the vendors have, this is of course purely empirical, right? We can get 4 bits, 4 random number generator bits out of a single bank. Whereas one vendor, you cannot get that. So this is an indicator of the quality of randomness, because clearly you cannot get 4 bits that pass our tests. There's some difference, but we don't know why that difference exists also. I think my guess is actually the difference probably exists because that vendor perhaps didn't scale as fast as the other vendors to smaller technology nodes. But again, this is speculation. If you're interested, look at the paper. There's a lot of data. But I don't want to spend the entire lecture on that. Okay, any other questions? These are very good questions. Otherwise, I'm going to not talk about refresh latency reduction, but point you to a paper that talks about that. And if you're interested, you can take a look at that. I guess I did a terrible job copying and pasting. Or maybe there's something underneath this one. Anyway, I'll figure it out. Okay, so let me actually not switch gears, but we're still talking about reducing latency, but I'm going to give you another way of reducing latency over here, which doesn't, if the DRAM is built without a lot of internal timing assumptions, which shouldn't require changes to the DRAM itself. But unfortunately, existing DRAMs are built with some timing assumptions internally, where they're self-timed. As a result, you cannot do what I'm going to describe in existing DRAM chips, but there's no reason why you cannot do it if you don't have those timing assumptions that are internal to the DRAM chip. Okay, and I'll give you the executive summary to begin with. Basically, our goal was, of course, we've looked at a lot of things, right? But a lot of things require changes to the DRAM chips. Not everything, ALDRAM doesn't. But this, we wanted to do something different. Basically, we wanted to reduce the DRAM access latency with no modification to the existing DRAM chips. And there are multiple observations in this paper to this effect. One observation you already know, a highly charged DRAM row can be accessed with low latency. If you already charged it a lot, you can access it with low latency. That's very similar to ALDRAM. A row's charge, but the second observation is that a row's charge is restored when the row is accessed. Meaning that when you access the row, you really replenish the charge. You're refreshing the row. Actually, a row's charge is restored when the row is refreshed as well. That's true, but when the row is accessed, is much more interesting, as we will see, because a recently accessed row is likely to be accessed again. Now you can actually put all of these things together. Well, this last one is called row-level temporal locality. This is really an indication of bank conflicts, right? You accessed the row recently, you activated it, and then you had to close that row because some other row needed to be activated, and you go back to the initial row that you activated, A and B, right? Which means that the A becomes a recently accessed row, and it's likely to be accessed again because there are patterns and programs that lead to row-level temporal locality. And this paper analyzes that a little bit. So the key idea, if you put all of these things together, you can come up with this neat key idea which says, why doesn't the memory controller tracks recently accessed DRAM rows and use lower timing parameters if such rows are accessed again? Because you know that you recently activated it, there's a lot of charge in that row, and if you access it within 1 milliseconds, let's say, it didn't lose a lot of charge. You can access it with lower latency. That's the idea. That's the idea of charge cache. And this requires no modification to DRAM if the DRAM is built right. And it's low cost. It doesn't change DRAM. And it gives you high performance because you're reducing the latencies. Of course, it's dependent on the workloads you're assuming. So I think it can actually buy you even more performance. And it reduces DRAM energy because you're really reducing the access latencies plus improving performance at the same time. So I'll go back to this picture again. As you can see, we really like these pictures. So you have the cell, you have the sense amplifier, these are the voltages, and there's a ready-to-access charge level over here. And if you get an activate command, the sense amplifier kicks in, and at some point, the cell becomes ready to access, as you can see. And then you can do reads and writes at that point in time. Now it becomes ready to pre-charge, and you can pre-charge it. Okay, that's the idea. So this is some cell that doesn't have a lot of charge in it. It starts with this level for whatever reason, right? Because it wasn't accessed for a long time after it was refreshed, and it was like 40 milliseconds after the last refresh, assuming you're refreshing every 64 milliseconds. Now let's go back. These points shift to the left if your cell is highly charged. Right? As you can see, this is a very highly charged cell. Sense amplifier kicks in earlier, and also sense amplifier amplifies things much quicker because the cell was highly charged to begin with. And the cell reaches the ready-to-access level much earlier than this other cell that had less charge to begin with over here. And we're going to exploit that basically. You can issue a read and write much earlier, issue a pre-charge much earlier. So you can reduce the timing parameters for a cell that was recently activated or that has a lot of charge. Okay, basically a highly charged DRAM row can be accessed with low latency, and our simulations show that you can reduce the latencies a lot. This is in line with actually a lot of ALDRAM work. So, okay, the question is, how does a row become highly charged? Now let's take a look at what happens to DRAM cell. It loses charge over time, clearly, and there are two ways of restoring a row's charge. You refresh it, as you can see, meaning that if you access the cell right after a refresh, you can access it much faster. But of course, there is no refresh happens asynchronously or completely orthogonally to program accesses, right? there's no relationship, or intuitively there should be no relationship between when a refresh happens and when an access happens in a program, because these are completely independent processes to each other. But the other one is very interesting. If you actually access a row, you also increase the charge. Right? And because of locality in the programs, row-level temporal locality that I'm going to show, after you access a row, you're very likely to access it again. So we can exploit that a lot. So a row's charge is restored when the row is accessed. That's the second observation. The next question is, how likely is a recently accessed row to be accessed again? And it turns out very likely. We actually do a lot of analysis in this work that shows that that analyzes a fraction of rows that are accessed within time t after their previous access. And we look at different values of t. And this is workloads. I think these are single-threaded workloads in this case. Yes, and you can see that if t is 8 milliseconds, you can see that 86% of the rows are accessed within 8 milliseconds after their previous access. So it's a very high fraction. And this actually, anyway, there's some anomaly over here that's explained in the paper. It's not that important. Actually, if you are much more intensive in memory access, meaning that you have 8 cores that are banging on memory, a single channel, you have a lot of bank conflicts, this row-level temporal locality increases to 97%. So you're very likely to access the row again within 8 milliseconds after you previously accessed it. Again, this is an indication of bank conflicts. That's why all of the previous approaches that tried to reduce bank conflicts, like subarray level parallelism, work. But now we're going to use this to reduce the latencies. So the key idea is very simple once you make those observations. We want to track recently accessed DRAM rows and use lower timing parameters if such rows are accessed again. And the idea is called charge cache. It's an interesting name. I didn't like it initially, but then I grew to use it, I guess. It's not caching any charge. It's really caching the addresses of the rows that are highly charged, basically. So let's take a look at how it works. You get an access to row A. It's a miss in the charge cache. You haven't recorded. You use default timings. And then you activate row A. And then you record in charge cache that row A is accessed recently. And then you get an access to D. It's a miss in charge cache. You use default timings. And then you activate row D. And then you record in charge cache that you recently activated it, meaning recently you replenished the charge in it. Let's assume that you get an access to A again because of a bank conflict. This is a single bank in DRAM. Well, you check the charge cache, and charge cache says, oh, you recently activated it. It's a hit, so you use lower timing parameters for it. That's the idea. It's a very simple idea. It works. Not in real DRAM chips, because DRAM chips actually don't allow you to do this, interestingly. Okay, and then, of course, you need to clear the charge cache at some point because you don't want stale entries to be here. So periodically, you clear the entries over there. And we model it with cacti. Okay, you can read the paper for all these details. It's very low cost in the end. And we use RAM later in a bunch of workloads. And you can, again, read the papers for this. I'll just give you the high-level performance. So there's actually prior work that had this idea. Nice. This is an HPCA paper, I think, in 2000-something. I don't remember, maybe 2014. What it does is, it basically, after you refresh a row, if you have an access to it that's coming soon after, you can access that row faster. So it's partly the charge cache idea, but it uses just refreshes. I think as I said, refreshes are really asynchronous with program accesses. So it's hard to think that you'll be accessing a row that you're recently refreshed with high probability. Right? So, but it does actually improve performance, as you can see, right? There is some performance benefit because it just so happens that the program accesses some rows that are recently refreshed. But the row-level temporal locality is much stronger than refresh-level temporal locality, let me call it that way. You get a lot higher performance improvements in most applications, as you can see. But you get even better performance improvement, of course, if you combine these two ideas. These two ideas are completely orthogonal, and you can combine them. And the upper bound is low latency DRAM, so we don't get close to the upper bound in some workloads because the charge cache size is not as big. But if you increase the charge cache size, which is in the paper, you get closer over here. Upper bound is you always access DRAM with the lower timing parameters that you use for the rows that hit in the charge cache. Okay, you can read the paper for more detailed. And 8-core performance is even higher, of course, because these are more memory-intensive workloads. Okay. And energy reduction, there is also, as I said, whenever you reduce the latency, you also reduce energy because you activate things for much shorter. You drive the bit lines and word lines much shorter time. And also, in this case, you're improving performance, so you're reducing the leakage power. Right? And if you want to learn more, the paper is here. Any questions on this? Yes, please.
So I just want to ask about your assumption of, you assume that after 8 milliseconds, the row will be accessed again. Is the 8 milliseconds is the deterministic, or does you randomly?
So we do this analysis for different t's, different values, and 8 milliseconds tends to be a nice value. But in the paper, we analyze, for example, after 0.125 milliseconds also.
Does it depend on the instruction frequency of the CPU? Like after a certain instruction, it will access the row again?
I see. Yeah, certainly it depends on what you're executing, right? It depends on the program. If the program is accessing a particular data structure within 8 milliseconds, then you capture this locality. Assuming, of course, it leads to all of these bank conflicts at the bottom. But if the program is accessing the data structure at every 9 milliseconds, then you're not going to capture that locality. But we wanted to, this is also, how you set this is also dependent on how much you want to reduce the DRAM latency as well, right? Because if you want to ensure that you reduce the DRAM latency after 8 milliseconds, you need to find the reliable DRAM latency because you lost charge for 8 milliseconds. And you want to find that reliable access latency. Right? So you can actually use 1 milliseconds and reduce the latency even more. Or you can use 8 milliseconds to reduce the latency less. Or you can actually be more complicated and keep track of what rows, 1 millisecond, how much has it been since the last access or the refresh to the row, and have a latency table that associates that time with the latency to access. Right? But of course, that's more complicated. Because you don't want to be wrong in this case, right? If you're wrong, you get bit flips. That's a very good question, though. Yes?
Regarding you're using the temporal locality, but are you considering that if you have some intermediate level caches, you don't access to the same location of the DRAM when it's already stored in the cache?
Yes, it's already modeled over there. So if you hit in the cache, you're not going to go to DRAM.
Yes.
But there are cases.
You are directly accessing the DRAM from the CPU, right?
No. In this case, we have caches. They're all modeled. But there are cases where the caches miss.
Yeah.
Because cache block size is 64 bytes, whereas the row size is 8 kilobytes.
Okay.
So cache may have cached one of the blocks, but not the other block, right? So that's the kind of locality that we're capturing. It's a row level locality, not cache block level locality. That's a very good question also. Okay. Yes?
Does it indicate that something could also be improved in the cache system?
Yeah, I think so, yeah. So basically, I think this is an indicator that, something can be improved in the DRAM system also, but also the cache system potentially, but not, maybe in the prefetching system, right? Because what you're doing here is, the cache system is doing the caching with 64 bytes, and it's doing well actually, but you're really accessing some other cache block in the same row. Maybe if you can somehow figure out which blocks you're going to access, whenever you open the row, you access them, like 4 blocks, before you actually get the request. And then you cache them, and then you don't get another request to DRAM, right? So it's really, I think of this as a prefetcher. If you can build a prefetcher that can guess all of the possible blocks that you need from a row that you opened, you might want to do that when you open the row, right, at the first time, and then you open the row only once and never again. But that's not easy to do. There are works actually that looked at that sort of thing. It's called spatial pattern prefetchers. They basically try to find a spatial pattern in Yeah, in the DRAM system. But they work with low coverage usually. And their accuracy is questionable. But of course, people can build new prefetchers. Okay, so we have other works in this area. I'm not going to go through this, but this actually looks at partial restoration. This is even more complicated. And you can look at the paper. But now let's summarize a bit. How much time do we have? Well, I'm taking longer than I expected, but it's good. We have some interaction. Let's hope that we can finish emerging memory technologies today. So, okay, let me summarize, and then I'm going to do a little bit more something else, and then we're going to conclude. So basically, we've covered all of this right now. Hopefully it's interesting. I think there needs to be more ideas, because as I said, latency reduction is not a lot in DRAM. And in different DRAM types, latencies are increasing. But latency, I think, is a really good focus area going forward. So we need to be looking at more fundamentally low latency computing architectures. Okay, while we were looking at all of this, we also wanted to look at power consumption. I'm going to briefly talk about some of the studies that we've done in this area, because it turns out, surprisingly, there wasn't a lot of work that really measured real DRAM power. But with our infrastructure, we can expand our infrastructure to do power measurements, and this is a fancy picture of it. That one, the one that can do power measurements. So actually, this took about 1.5 years to build. We didn't get it right the first couple of times. There were a couple of undergraduate students who worked really hard on this, and unfortunately what they built didn't work, so they helped with the next one, next generation. And then we were able to measure power nicely. Okay, but you can read the paper for more detail. Unfortunately, we don't open source this because it's a bit expensive. But we cannot also manufacture it for you. Okay, anyway, I think this is very interesting. The SoftMC is open source. You can actually build this infrastructure yourself. But what we wanted to do is we wanted to measure current consumed by a module during a test that you do using the SoftMC infrastructure that we have. And we tested a bunch of DDR3 low power modules, about 200 DRAM chips. And we basically did a lot of tests. You can look at the experimental method. We wanted to understand the power consumption of these modules with real tests. And there are very interesting observations. I'm going to go through some of them very quickly. Clearly, we're at page 86 out of 20, as you can see. So it's interesting that this dynamically changes. I'm not sure about dynamic, this changes somehow. Somebody needs to fix PowerPoint. Okay, so this is one example. Basically, one of the observations is that real DRAM power varies widely from the values that are specified in the data sheets. Data sheets tell you something, but that's not real. That's not real in the sense that real DRAM power is actually lower than what's provided in the data sheets. Data sheets are very conservative. So as you can see, the data sheet values are very high, but what we measure is actually relatively low. Again, this could be because of the margins that are added, right? And different vendors have very different margins. So there's low variance among different modules from the same vendor, as you can see over here. Okay, so that's one of the observations. You can see more detail in the paper. One of the other observations, which is not that surprising, I think, right now, is DRAM power is heavily dependent on data values, because a lot of things in DRAM is dependent on data values, including retention time. Power is no different. Basically, this is number of ones in a cache line that you have, and this is the read current that you see. And it increases with the number of ones in a cache line because it's more expensive in terms of power to transfer ones in the DRAM interface. And of course, this measurement is not easy, and the paper has some detail related to that. Okay, and the write current is also actually exactly the opposite, because you're driving the charge in a different way. Okay, there's a lot more information in the paper that I'm going to skip over, but essentially the key takeaway is DRAM power consumption depends strongly on the data value. And I think now you have a power model for that, meaning that you can actually propose an encoding, data encoding method that minimizes the power, and you can actually figure out how much you can reduce the power consumption with a different kind of encoding of data. We did not do that. We proposed that as a particular. Actually, we did do a very preliminary experiment in the paper, but I think there's more work to be done in the encoding of data inside the DRAM to minimize power consumption. Okay, this is also interesting. Again, this may not be that surprising, because we already saw that there's structural variation in terms of voltage, and that's true for power also. Structural variation leads to power variation, and you see basically this variation across different banks of different vendors. You have significant variation in read current, for example, and idle current across different banks. So DRAM has these different currents, basically. If the DRAM bank is idle, you need to supply a different amount of current to keep it ready for access. If the DRAM bank is being read, you need to supply a different amount of current so that you can read it. If you're writing, you need to supply a different amount of current. So if you look at the data sheets, they specify, I think, at least 9 or 10 of these currents. And that's how we do the power measurement. We look at these currents, actually. And there's a data sheet specified power current, and there's a current that we can measure with our infrastructure. And this is also interesting. There's some variation you can see in terms of the activation power. And this is based on the row address. Somehow there's spatial variation that you have based on the rows in the DRAM in terms of power. So basically, the takeaway is there's significant structural variation. DRAM power varies systematically by bank and row. Okay, this is interesting. This is, even though there's a lot of margin in the data sheets in terms of power, the data sheet values that show that DRAM power is reducing significantly over manufacturing years, but we don't see as significant of an effect in the measured power, meaning that generational savings are smaller than expected if you look at the data sheets. So this is activate pre-charge power, IDD0, that current. You can see that the expected decrease is really 192 milliamps, but we see an increase actually over here and a decrease. And these are based on many, many measurements. Of course, it's not, we cannot explain exactly why this is happening, right? You can only say that this is happening. And that's happening across many data points that we see. So basically, the takeaway is actual power savings of newer DRAM is much lower than the savings indicated in the data sheets, which is interesting. Okay, so this is just a summary, and there are more observations and detailed analysis in the paper. So based on this, what we wanted to do is, all of these measurements, we wanted to actually build a much more accurate power model for DRAM. And we built this aptly named power model called Vampire. It's a very constructed name, as you can see. A variation of a model of memory power informed by real experiments. I guess my students are very creative. Basically, what this does is it takes inputs from a memory system simulator, a trace of DRAM commands and timing data that's being written, because clearly data affects the power a lot. And you feed it into this power model, which is open source. You can use it. And this does some new modeling that's not existent in other modeling. So a lot of the data power models that exist use data sheets, for example, which are wrong, as you can see, or which are conservative, as you can see. So this does read and write and data-dependent power modeling, different types of currents power modeling, and structural variation aware power modeling. And it basically gives you an output per vendor power consumption and a range for each vendor if you want it. And you can download it and use it. And if you find bugs, please let us know. Basically, we'll update it. That's how our open source work usually operates. Basically, it's good to put it out to the community because clearly there will be bugs in anything you put out. It's good to get that feedback from the community. And we actually, for Remulator, for example, we got a lot of feedback from companies that are using it, and we incorporated in the Remulator, so it helped everyone. Of course, companies are using it internally without telling us why they're using it, but it's good for everyone if these things are open source. Okay, so let's take a look at the error rates that you get in these power models. So these are the two commonly used power models. And we actually used DRAM power in the past. DRAM power is, I believe, a good power model that's used by Remulator. Remulator has automatic integration support to DRAM power. But a lot of people actually use what's called the micron model, and it's really based on datasheet values. And you can see that this is the percentage error that you get compared to real device measurements that we've done. So the error rates are actually huge if you use the datasheet values out of the box. DRAM power tries to model the power as opposed to just trusting the datasheet values. So it does a better job, as you can see. Its error rates are relatively low, but it's still pretty high, especially for vendor A. And if you use Vampire, the error rates that we get are actually much lower, as you can see. Still, of course, there needs to be more validation done. But I think based on measurements, you can do much better in general, as you can see. Okay, so what can you do with it? Essentially, you can imagine new studies that can be enabled if you have this sort of power model that's good. For example, we propose some things. We don't evaluate all of them. You can take advantage of structural variation to perform variation-aware physical page allocation to reduce power. Basically, frequently accessed pages can go to low power parts of the DRAM, and I think it's a good idea. We just didn't evaluate it. You can do smarter DRAM power down scheduling, whatever that means. You can read the paper. This is the encoding study that we did very briefly. Basically, you can reduce DRAM energy with data dependency aware cache line encodings. Essentially, you can optimize the encoding based on the results that we get. You minimize the ones, minimize the zeros, and you can see that you can gain significant energy reduction with the encoding that we propose. I'm not going to go into the details of the encoding over here, but this shows the potential benefits that you would get if you use one kind of encoding in DRAM. I think there needs to be a lot more work to be done in this case, actually. We just gave a proof of concept. We didn't solve all of the implementation challenges related to this encoding. And I believe there could be other studies if you have this sort of a power model that gives you the effect of data on the power, the effect of structural variation, and the effect of vendor dependence on power. You can do more studies. So it depends on people who are interested in their imagination and creativity, I think. Okay, and that's the paper that we written. It took a long time to actually get this paper. Get the research done, first of all. But this is actually never rejected. I can also say that there are papers that are never rejected, you know. Actually, the Sigmetrics folks really like this work, and yeah. Any questions? Is it interesting? Okay. You want to review this paper? Maybe. Okay, some people want, maybe. Okay, let me conclude. I think we've covered all of this at this point, actually. We're going to cover emerging memory technologies, which doesn't really fit into any of this. It's really something else. But let me draw some solution principles so far, very quickly. I didn't know where to draw these principles, but I think it's good to draw them right now. So basically, what we've covered so far, I think, points to we should have more data-centric system design and intelligence spread around. We don't want to center everything around traditional computation units. We want better cooperation across layers of the system. And I think this requires careful co-design of the components and layers, system architecture and device, better, richer, more expressive and flexible interfaces. We will see more of this actually in emerging memory technologies. I think maybe this is a bit premature to draw these conclusions, but I think based on what we've seen, we actually need this. Better than worst case design. So the lectures we've covered on latency and refresh point out to the fact that we are optimizing for the worst case in existing devices. The worst case is really determining the common case. We have basically one operating point, refresh every 64 milliseconds, everything. Or access with activate latency 15 nanoseconds, let's say. Even though you can do much better than that, basically. I think these design principles are really important. And also heterogeneity in design. Basically, we want heterogeneity, specialization, and asymmetry. There's no one-size-fits-all. This enables a more efficient design. And I think, for example, changing the refresh rate according to the cells requirements, according to the applications requirements, which we didn't really examine, but cells requirements we did examine, that introduces heterogeneity and that enables more efficient design. I think these are the really 4 fundamental principles that I could distill to summarize what we've observed so far in the 5 lectures. 5.5, I think, at this point. Data-centric system design, better cooperation across layers of the system, better than worst case design, and heterogeneity. If I have to make it more compact or shorter, I'll probably put it this way, basically. Data-centric design, all components intelligent, better cross-layer communication, better interface. We're going to talk a little bit about that before we take a break. Better than worst case design, heterogeneity, flexibility, and adaptability. I think all of this requires some open minds, actually. One of the things that's missing in industry is open minds sometimes. So if you go to industry, change that, please. And of course, this is also dependent on the culture of the industry. Sometimes there are open minds, but they're pushed out of the culture because they're too open-minded. Yeah. Okay, but as researchers, we should always have open minds. Okay, let me talk about this because I think this relates to something that I said over here, better cross-layer communication and better interfaces. I think this is a really, really important problem going forward. And I'll give you just an example of it and reference the papers that I already mentioned But if you're interested, you should definitely take a look at those papers, because this is something that is relatively new that we've started over the course of the last 2 years. And I call this data-aware architectures in general, but you'll see an example. Essentially, what does this mean? We talk about data-centric architectures, which is processing in memory, for example, or putting data as a first-class citizen. Low latency, low energy access to data, that means also in terms of data-centric. We talk about data-driven architectures briefly, the example of using a lot of data to make decisions, like reinforcement learning-based memory controls. I call that a data-driven architecture. Well, we didn't talk as much about data-aware architectures, although we did give a couple of examples. Basically, I think a data-aware architecture understands what it can do with and to each piece of data. So it makes use of different properties of data to improve performance, efficiency, and other metrics. If you remember the heterogeneous reliability memory, we basically specified, oh, this data can be reliable, this data doesn't have to be reliable. Now, you can design an architecture that can allocate those data to different types of memory and improve performance and efficiency and cost, whatever, right, while keeping reliability in check. But there's a lot more to this, because there are many, many different characteristics of data, right? Data may be compressible or not compressible with different compression algorithms. Data may be approximable, meaning that you can approximate it and you don't lose much. And there are different levels of approximation, potentially. Data may have different types of locality. As we've discussed, they may have row-level locality. They may have some other locality, spatial locality, temporal locality. Data may have sparsity. It may be very sparse. It may be very dense, especially in matrix operations. We see this a lot, actually. And you really want to treat them differently. If you have sparse matrices, you have a lot of zeros. You don't really want to waste your time doing zeros, for example. And there are, of course, correlations between these also. Data may have some different criticality for different computations, right? This particular data element, for example, is a lock that's shared by many threads. And that information may be available at the higher levels, right? Data may have some access semantics, right? I know it may actually have some shape. Like if you actually have some matrix, it may have some dimensions, it may have some tile sizes that the programmer intends. So there are many, many properties that data has. And if you think about this, this information is visible, or it can be gathered at some level, especially at the programmer, compiler, higher levels of the system, right? But what happens when you go into the hardware level? None of this gets communicated to the system or the hardware, right? I think it's good to rethink this, the way we're designing systems. We have so much information that's available at the top, and yet we're funneling that information to these bits. And those bits are called instructions and memory addresses, and not much else really. Yes, there are some hint bits that people try to add, like prefetch instructions, for example. These are very, very specialized examples of communicating these some higher level semantics down into the hardware, but they're extremely specialized, and they require basically separate interfaces, separate instructions. So as a result, it becomes a mess, and they don't become adopted very well, I think. For example, people proposed a lot of cache hint instructions. They're sometimes used, sometimes not used. It becomes a mess, I think. So basically, we have this interface, software-hardware interface, that's today very narrow. This higher level information, I mean, this gives some examples over here, but clearly I've shown you more examples. And in the paper that I'm going to reference, you see even more examples. Even the data type information sometimes doesn't get communicated. If your ISA doesn't have the information about the data type, like how you're accessing this, is it a queue, is it a stack, is it something else, is it a tree, that information doesn't get transferred into hardware. Basically, we have this very narrow funnel today that eats up all of the higher level semantic information and basically spits only bits that do not provide much information at the lower level. So we want to change that, essentially. I think if you want to really have a much more scalable and intelligent system, you really want to change that, and you really want to make this higher level information, and I call it the data semantics, visible to the hardware. So basically, we want to make this interface much more expressive. And I'm not going to tell you exactly how we do it. If you're really interested, maybe we'll talk about it at the end. But this is called expressive memory. And it's basically a different way of organizing information related to data. It basically takes, divides memory into chunks, and it basically associates characteristics with those chunks. And you can read the paper for more detail. The paper talks about what kind of characteristics you can assign. Clearly, it doesn't assign all of the characteristics, but it's a general purpose mechanism to assign characteristics to different memory chunks. And those memory chunks can be interpreted by the hardware. And the hardware, or actually there's this also system component here. It's not just the hardware, it's also the system. Now the system and the hardware can read those chunks and say, okay, oh, this data that is associated with this chunk is very compressible. So I'm going to compress it. Or this data has very streaming characteristics. I keep streaming over it. So I'm going to actually allocate it in a memory that's good at streaming. This data is very random access. I'm going to allocate in a memory that's good at random access. So you can actually imagine many, many optimizations. And the paper talks about some of those optimizations. I was going to say something else. I guess I'm going faster than I can think. Okay, so this is a general purpose mechanism. And also you can change these programmatically. Basically, in the program, you can insert instructions saying, okay, I'm changing the properties of the data at this point. So it's visible to the programmer, which means that if the programmer has some information or the compiler has some information, they can basically say, okay, the properties of the data has changed right now, so map it to something different. So you can actually program this. And I think none of this exists today, and that's exactly what we want to change. And if you really want to know more, this is the paper that we've written. It appears last year, ISCA, and talks about essentially expressive memory. It's not, and the key takeaway is we want to cross these abstraction layers such that we can communicate this very rich information that's visible at the higher levels to the lower level, so that lower level can do a lot of optimization. For example, this paper, I don't think this paper does justice to the evaluation. I think the high-level idea is great, but the evaluation itself doesn't show the full power of this sort of interface. In the end, for example, one of the things that it shows is if you communicate the tile size nicely when you're operating on matrices to the lower level hardware, now the hardware can make decisions to do caching or prefetching based on the tile size. So the programmer doesn't dictate exactly what goes where in the caches, because programmer may not know what resources are available to the program itself. For example, if you're sharing bandwidth with some other program, the programmer has no idea about that. But the hardware has a lot of that idea, except hardware is currently missing the information about what is the tile size that you need in a cache, right, for a particular matrix. If it has that information, now it can make intelligent decisions about, okay, I need to actually keep this tile in the cache. How am I going to keep this tile in the cache? So the paper evaluates that use case. I think it's a very good use case. Another use case the paper evaluates is if you know the access characteristics of different data structures, you can actually, for those data structures that conflict in DRAM banks, you can allocate them to different DRAM banks if you're accessing them at the same time. So that's another use case that it evaluates. So it shows actually performance improvements, but I think the performance potential is even more because we cannot evaluate some of these things easily because it requires a lot of infrastructure actually. So we now have an FPGA version of this built on the RISC-V processor. So we're looking at more evaluations in this area. So if you're interested, take a look at the paper. I think this is going to be, it's going to change the hardware-software interface into the future. And we really need to rethink that interface. Yes?
I want to ask, when you write cross-layer abstractions, so how can we define the abstractions? Do we do it automatically or we need to define it manually?
You mean these properties of data?
Yes.
Yeah, so that's something we don't solve over here. Some of these, I think some of these have to be manual, some of these can be automated. Yeah, exactly. So if it's automated, it's better, of course, for the programmer. Mm-hmm. If it cannot be automated, I think programmer still has a lot of information about the workload.
Okay.
Yeah.
And there's this method for every kind of programming languages, or now you focus on it one.
Yeah. So in this case, we don't tackle the programming language part. What we tackle is really the hardware-software interface part. So how do you actually put this in assembly? But you can, of course, you need a programmer to communicate that to the assembly language somehow. So I think there needs to be some substrate that's built on the programming language that takes advantage of what's underlying here. So it's in a sense, it's programming language agnostic. If the programming language provides that information, it's general purpose enough to communicate that information down to hardware. Okay. Okay. And we actually, this is more general purpose, and we actually have another paper in the same ISCA. Nandita, my student, is the first author. And we did this work with NVIDIA, and we showed that actually in a particular example of this. It's called the locality descriptor. It's an example cross-layer abstraction to express, well, I guess it's the title, to express data locality in GPUs. Basically, the programmer expresses different types of data locality in GPUs, whether it's cache locality, whether it's inter-thread locality or intra-thread locality. And that information gets communicated to the lower layers in the GPUs. And the GPU makes memory allocation decisions using this information. And I think this is really interesting. This is a very concrete use case. It buys you a lot of performance, actually. For example, a lot of GPUs have non-uniform memory access systems right now. And if you have locality information, you can allocate your data nicely. And internally, NVIDIA is actually implementing a version of this because they saw a lot of benefit from this. And you can read that if you're interested. How many people are interested about GPUs here? Okay, somewhat. I think it's good to look at GPUs for sure. Okay, so I think I've covered all of these so far. We didn't spend a lot of time, but reinforcement learning-based memory controllers is one example of this. I think we're almost done with this lecture. Okay, let me switch this because I already said this in the other part. But I think what I just described actually spans across the layers also, and it really cuts to the heart of this over here. How do we design a better hardware-software interface? If you look over here, I think processing in memory requires a better hardware-software interface also. I didn't say that, but this sort of expressive memory is also very good at processing in memory because you can specify the information about a code chunk based on information at the higher levels. You can specify that, oh, this particular data is very good at keeping processing in memory, for example, right? We didn't do that again. But I think that sort of interface enables that. And that brings us to the end of the low latency memory. Right on time, I guess. I expected only 1 hour, but it took 2 hours. Any questions before we take a break? Because I think it's a good idea to take a break. It's a bit warm here. Maybe you get better AC over there. Okay, so let's take a break. Let's be back after 10 minutes.